Hi, in this video I'd like to introduce so-called integrating factors of differential equations in differential forms. In this part 1 especially, we look at this very general cases. So let me first start with this example. This is a Cartesian equation, and I hope you understand how to deduce the differential equation in differential form from this Cartesian equation. Namely, we're going to take the partial derivative of this one and put it in front of dx, and partial derivative y and put in front of dy. So I did that down here. Since we go through the product rule of this left hand side, it's kind of lengthy calculation, so you may pause the video, actually do this calculation yourself, because knowing the detail, the shape of this one is really important. So if you do that yourself, and you will understand far better. Now, I hope you have the same thing and I had, and then I apply the product rule. And when you do this power part, especially, you have to use the chain rule, so you have to be careful about this part. It is definitely the consequence of having this multiple power. Then there is a second power still appearing in the first term in here, and there is a one power still appearing in the second term, and same phenomenon for the coefficient of dy as well. I forgot to put 0 here, but there has to be this equal 0. Sorry about that. So if I expand this polynomial and give it to you, and expand this polynomial and give it to you as a coefficient of dy and dx and dy, then by going through this curl calculation, my minus nx, you will be able to see that that's 0. So expanded version, you can go ahead and try to integrate, and you'll be able to succeed. Right? You're guaranteed, because of the curl 0 locally guarantees that it's exact. So there will be two variable function whose partials are this, and that's going to work. What happens is that because we set this one equal to 0, I realize that I have to put that thing in there so that following process makes sense. I realize that I had that 0 in the next line, so I'll keep it there. The key thing is that there is these common factors. So first power is a factor. So if you cancel those factors, it changes the coefficient a little bit. So this is what happened. Well, actually, I simplified. So if you cancel that, we have a first power. If you cancel that, we only have 2x plus y and 2x there. So so it's a perfect spot to use my pen tool, so I did that. So as you cancel that, this disappears, right hand side of 0. So we have kind of slightly simpler equation, and I simplified it. It looks like this. So I forgot, I put the dx down here, and the bottom here looks like this. So that's our new differential equation in differential form. And then I calculated down here with this new m and n. After we factored out, you can see my is not equal to nx. It's supposed to be x there. Sorry about the mistake. The correct answer is 2x minus 2, and still not the same. So you know this is not exact anymore. So you cannot integrate this one and do that. It has to be exact. Of course, if you knew what was factored out, canceled out, x squared minus y, you can put that back in, and you'll be able to see that's exact, and effort of integrating will work. But if you don't know, and by just staring at this one, you somehow you have to figure it out what this x squared minus was. This factor here will multiply back in there, turn this non-exact differential equation to an exact equation. That factor to multiply here is called integrating factor. So here is x squared minus y. Will do the job because we know it. But if you don't know, in the effort of trying to find the integrating factor, there can be multiple answers. There is no unique integrating factors. Yet, that's going to lead us to the unique solution. Actually, we'll be able to sort out one of the solutions. As you do too much, you can have too much possibility down there, so you have to sort it out which is the right solution. But usually you don't do too much. So from here is a general discussion, and from there we're going to deduce a very important formula that will help us to figure out what the integrating factor is, what to multiply here such that this becomes exact. When you check it right now, this is not exact. So We have to figure out that vector. We're going to call that I. Now I multiplied it. We don't know what those are, but if you assume there is a factor, that I, if you multiply here, now this becomes exact. So how do we detect this one being exact? Is the curl, you differentiate this whole thing in front of dx with respect to y, this part with respect to x, they should be equal to each other. So we go through product rule. If you differentiate this one with respect to y, then through the product rule, and this is what you get. And that part, through the product rule, this is what you get. That's I. And we want to solve m and n are given, therefore this m's partial y and partial x, these can be computed. So what we're looking for is this I in there, and iy, the partial derivative of unknown function I, two variable, partial derivative x, unknown function of I. So those are, so you end up at partial differential equation. Try to group this nicely so that we can see clearly what to do. So I collected those I part in the left hand side. Here's the IMY. I part is NX on the other side, pick up negative. Here's the IY. It's here, now it's on the right hand side, therefore I picked up negative there. And this was already there. So it's organized like this. Again, M parts are known and everything with I is unknown part. Here's the next nice thing part, that I divided both side by I, so I goes to denominator. So I nicely isolated. Left hand side is completely given, you can calculate that. Right hand side we have M known and N known, and in front of it is just a coefficient that's unknown. So we're going to stare at this one and figure out how we're going to write this derivative, curl, in terms of combinations of m and n. In general, this is going to be very difficult, but if there is an integrating factor that are very simple, but by looking at it here, that didn't come easily to us, then maybe it is possible to look at this explicit one and try to combine m and n and think about very simple possibility in front of here and figure out that works. So that's in general strategy. But if often if you just write down random two things, m and n, and there's no hope that you can solve this partial differential equation at this stage in general. So first we're going to approach inspection method for this general case. So let me formulate this partial differential equation slightly different. Idea is that this part here can be rewritten a slightly simpler form. I is in the denominator and partial derivative is in the numerator. This is quite well known. This is really derivative of logarithm, and this is derivative of logarithm. And that is the motivation to write this IYI as a derivative of logarithm I, derivative of the logarithm x. So we're just going to simplify this ln I as a j. So that part is going to be just jy, and that part is going to be the partial derivative of jx. So this whole thing is now has new notation, just jy, and that's a jx. So that makes this entire thing slightly simpler and nicely isolated and separated. So that's this equation. There's this curl equals combination of m and n such that these coefficients are the partials of some same function. We can probably stare at this one and try to come up with this combination. Maybe that's very simple, but there's not these coefficients in front of m and n cannot be just an arbitrary. There's a strong relationship between these two. These two came from same function of the partial derivative of the same function. How can we actually detect that? It's a Clairaut's theorem again. Okay, this is what we're going to do. We compute this my equals nx minus nx, the curl, and you write down m and n there, and think about all possibilities of what to put in front of m and n, these functions, such that it equals that. For example, simply you can just put 0 there and take this b to be this whole thing divided by n. Or you can take that part b0 and you can figure out what a is. So extreme case, there is this obvious thing in front of us. But this a and b cannot be just arbitrary. There is this strong condition. So let me show you the Clairaut's condition here. So this a is supposed to be negative of partial y, b is supposed to be partial x. So what is this relationship with this a and b is going to satisfy? Is the following. If you differentiate this one with respect to x, that's going to be jyx. If you differentiate that with respect to y, that's going to be jxy. By Clairaut's theorem, these two is going to be the same, except there is this extra sign there. So if you actually add those two, then they're going to disappear. So this should be satisfied. So again, you write this linear combination, and there are many choices of a and b, but we have to look for the choices such that this ax plus by is going to be 0. Once you have that, and it's guaranteed that you have a j. And once you calculate the j, integrating factor is simply e raised to that j you found. So that's the algorithm. And computing this AB that satisfies this one, and I was saying there's just pure inspection. If there is a simple integrating factor that is involved in here, and we should be able to look at it here by inspection. So this is an example, and it's a bit general, so it might look like a lot of work, but if you actually try yourself, it's not that bad. All right, we're going to try it here. Of course, we're trying that because it's not exact, so we're not going to check that part, but we're going to calculate the curl anyway, so you'll see that's non-zero. All right, here it is. My is -6, and x here is -2. So that's something you have to check. It's not equal to each other. So here I'm showing you that thing again. We're going to write this my minus nx and try to write as linear combination of m and n such that this ax plus by is 0. So I'm going to put it up there. So ran out of spaces, I'll show it later. So this is the part 2 minus 6x, that's the my minus nx, and we want to write this as a times m and b times n. So m is here and n is there. The many possibilities. Sometimes you have to deal with 1 over x and 1 over y to match it. Sometimes you can just play with the polynomials. So we're going to try with the polynomials. If that doesn't work, and you have to think about 1 over x and 1 over y and here and there. Those are the simple cases. If those simple monomial or simple reciprocal doesn't work, then you have to look at the general case and then search for that one. It's quite calculation. So we are only doing this whenever there's a simple integrating factors out there that we don't see it easily here. So the game is inspection with a simple polynomial case first. If that doesn't work, we're going to go to simple reciprocal case. So we're going to focus on this, solving this PD right here with that extra condition. So I put it up there. We should definitely try constants. You put constant there, A, constant there, B, see if that's going to work. Here, if you put constant and for that spot of capital A and capital B, this is obviously satisfied, so you're good. So let me explain how I got this B must be 3 if this is a constant. If you look at the B is multiplied to -2x there, and you can see A's constant is multiplied here. There's nowhere there's going to appear that x alone, like -6x. This is the only possibility that you're going to get a -6x. That B must be 3. Once B is 3, then if you look at the constant part, only constant here is -b, and only constant here is a 2a. That constant should work out as 2, so that's why these 2a minus b have to be 2. It's like pretty much like the partial fraction decomposition. You have to look around, figure out quickly what those constants should be. Well, then capital A is 5 over 2, so that's what we have to figure out there, 5 over 2. But if you look at other term, you compare the other term, this makes no sense. That is not going to do it. So we move on to the next possibility. So let me show you my thinking on the next candidate. This is not going to be constant. Constant doesn't work. So I'm going to throw in linear polynomial, x or y. Okay, I'm showing this condition again, and this is the key condition. All right, suppose I'm about to throw in linear part to a to avoid the constant case. Okay, the thinking is that are you going to throw in here x or y? I throw in y here because we have to satisfy this condition. If I throw in x there, this partial derivative will have 1 in there, and this partial derivative is constant. It's going to be 0. It's not going to satisfy, so you don't even have to try that x. What you want to try here is if you throw in b, then this one with the partial derivative of x is going to be 0. That one's 0, so that's satisfied. So when you choose this thing, there's even, for example, if you keep the constant here, there's always some limitation that's on a. So that's good. That narrowed down the things to try. So let me explain why this c has to be 3. The equation's there. C is a constant. Now a is there. If you look at this a part and this, if you look at this negative 6x again, that c is going to be multiplied here. That gives you 6 part. But a is multiplied anywhere. It's not going to give you any first degree x. If b is multiplied everywhere, you're not going to get any x to the first term here. So that must be 3 again to match the negative 6. So what about a0 equals 0? Well, there are different ways to look at it, but I think what I looked at a0 is somewhere here. That's 3 multiplied there. So we get various terms. But if you look at it here, when by is multiplied here, you will get all the y terms in it. When you multiply a in there, you will get constant times all these things, but you will never had 12x squared here, so you had no choice that this part will pick up 12x squared unless a is a 0, so a should be 0. Once a is 0, only by is multiplied there. So by here multiplied to 12x squared, y, I don't see any 12x squared y, and you're not going to get any x squared y here, so that has to be 0 as well. Well, obviously, this a0, b0 knocks this thing completely down, and 3 times this is just not that. So this doesn't work. Alright, throwing in some linear term to a didn't work, so let's try to b there. So again, keeping a as a constant and try this linear term in there. This is going to be partial 0. So we want this thing to be partial 0 as well. So differentiating with respect to y, we want to throw in x term in there such that this is satisfied. Now this is what we got, and see why this b. So a is a, and this b part here, that's this part, it's going to be b plus cx, and see why this part has to be 0 right there. I think I looked at this b times y. You're going to get, as you multiply through, you're going to get all the x in there, and you're just going to pick up b times y, and there's no other possibility that with a constant little a, you will pick up y to the first. So that must be 0. Because when you look at the result, there's no y in there, that we're comparing this one with this curl. Then I wrote c must be 6, so b is gone. 0. I think I was looking at this cx times negative 12. So that's x squared picking up. There is no b anymore. X squared, that's the only x squared that's pop out. And as a constant, there's this x squared. So it must be 6 there, so that is negative 12 x squared. Positive, possibly it matches this one. Maybe that's not why I put 6 in there. I got it now. I looked at the cx to multiply to negative 1. That's x to the first term kicks in, but here there's no x to the first term. Everything has y or x squared. But if you look at the x to the first, negative 6, so this c must be positive 6, so that this matches negative 6. That's the only possibility for c. Then I wrote 2a equals 2, so we know the 6 there. Okay, I think I got this like this. This x is multiplied. There's no way you're going to get constants out of there because b is 0. Only constant that pops out of here is 2a. that must match the constant on the left-hand side. So a must be 1. Like that. So that's what we got, and see if you plug it in here, see if it really matches this 2 minus 6x. So I got this a 1, so a appeared there in front of that, this part right here. Then we got b equals 0 and c is a 6 and 6x, and that's what we got. So you expand it out. Then we have 6xy, that's negative 6xy, it's gone. We have negative 12x squared, positive 12x is gone. So we have 2 minus 6x. Bingo, we got it, 2 minus 6x. So we found it. If a is little a and b is b plus cx like this, obviously it satisfies this one to be actually 0. This is derivative 0 and that derivative is 0. So effort of calculating j here will work. The negative jy will be this one and jx will be that one. So let's figure out j part. So I summarize it here. We looked at first 2 minus 6x, that's the curl part, and was looking for what should go in front of this m and n so that it is two things equal, and 1 and 6x satisfied not only that part but also that part. So we got this one. Then we're going to set that a, negative jy, and that 6x and jx, and you'll be able to figure out a j, and that integrating factor is e to the j. So here's that process. The negative jy is this a, which is 1, jx matches 6x. So if you try to integrate and checking these conditions, you will arrive at here. So j will be 3x squared minus y, and you can easily check this actually satisfies that. And there's many possibilities for j. So there's absolute constant c, but by choosing this one, what it really does is that you go in here, throw in an additional constant up there in the exponent. That's the same as multiplying e to that constant. Now we're multiplying this integrating factor to the original differential equations, so that constant multiplication doesn't do anything. So you can choose safely always this part 0. Therefore, the integrating factor is e raised to that power 3x squared minus y. So we got it. If you multiply this integrating factor to the original equation, the magic will happen. So that polynomial in front of dx and dy is written here, and I'm multiplying this integrating factor, e to the 3x squared minus y in there. So here we don't have to compute the kernel. That's going to be a work, but it's guaranteed that it's going to be 0. What you have to do is that you integrate this one and checking with this one to complete the calculation as capital F of xy. Remember, when you integrate, you always have a choice. Are you going to integrate this one first or that one first? This one first and checking with that one. Integrate that one first and checking with that one. If you look at, it's going to be a partial integration. If you look at here, when you integrate with respect to y, only y to the first involved and y to the first involved. But if you look at x part here, if you try to integrate with respect to x squared is involved, so it's more complicated. So I would choose this one that's simpler and with respect to y, and integrate this one with respect to y. So this is the setting that I first attempted that, okay, let's integrate this one with respect to x, and then I have to calculate, you have to integrate the whole thing with respect to x, keeping y as a constant, and you have to throw in this part. But first of all, if you think about this one, it's complicated partial integration by parts. So I gave up on that part and look at this partial, e to the 3x squared minus y, and y minus x. These are all linear, y there, and x are just constant, relative constant. So I thought I could do this integration by part on that one. So I'm showing you this integration by part technique that works nicely, so not going over all this technical detail. This is supposed to be covered in Calc 2, so there's nothing to particularly point out, except that you have to add this relative constant in x, because we're doing with respect to y. So if you do this integration by part, so which I want you to pause the video and do this one and check in yourself, but integration by part end up at here. And there's a phi x. Now you have to check this one with the coefficient of a dx, and this one should have, not only it matches what we calculate here, it matches the coefficient in front of dy. You have to put some information about dx. So you differentiate this one, is supposed to be exactly what's in front of dx. So I differentiated this one with respect to x. So that one becomes easily phi prime x, but this one have to use the product rule. So if you do the differentiation, this one, 6x picked up, derivative of 3x squared. When you differentiate, that one is just 2 with respect to x. So that's what we have. So I simplify that because this exponential part's always common. And this picks up 12x squared, negative 6xy, and here's plus 2, and phi prime of x. So if you compare that with the original equation, they're quite the same. This has to be 0. This is exactly, actually, that first term is exactly what's in front of dx, so that must be simply 0. So here, that with that 0, what you get is that this whole thing plus a constant there. So that's whole thing plus a constant. So that was the answer. F of x with this part with a constant, absolute constant. As you can see, that was quite a work. I mean, a lot of work to inspecting and actually calculating, and that's a general case that your integrating factor here was this pure two-variable function. That's a general case, and it's a lot of work. In the next part of the video, I'm going to show you that integrating factor that turns out it's just one variable, and slightly more special cases. But it has important application to the first order linear differential equation.